Moving on, we're talking now about problem number 16, and this is the only problem we're going to be doing that has to do with the Earth and its rotation. I just threw that in there because you're going to see this from time to time. Essentially, it talks about this villain who wants to slow down the Earth's rotation from an initial velocity of one rotation or one revolution every 24 hours. And if you calculate this out and change this, it becomes, if you work through this, it's 2 pi radians per revolution. And 24 hours is 3,600 seconds. It becomes 7.27 times 10 to the minus 5 radians per second. And he wants to slow it down to one revolution every 28 hours. Why you would want to do that, I'm not completely certain. But if you do the same, use the same calculation, you get 6.23 times 10 to the minus 5. Now, he's not that powerful, an alien, because he can only exert a force of 4 times 10 to the 7th newtons, which sounds like a lot, but it isn't a lot, really. So let's take a look at what effect this would have. If you look at net torque, so you're applying the force on the surface of the Earth, you look at the net torque, and that's going to equal the inertial moment of the Earth times its angular velocity. So that means that the angular velocity is going to equal the net torque divided by the inertial moment, and that's going to equal R, which is the radius of the Earth, over times the force that he applies, over the inertial moment of the Earth, which is 2/5 mr squared. This comes from that diagram in the back, and if you rearrange this algebraically, you end up with 5F over 2mr. Now, let's keep hold of that because we're going to need that. Now, the final velocity is going to equal the initial velocity plus alpha t, okay? Now we have alpha up here, and so if we do the algebra here, we move this down here, I'm sorry, not this, but if we take this equation and put that in for alpha, we rearrange, we move this over on this side and divide that by alpha, we get the net torque. So we take this, put it in for alpha, and then we rearrange this to solve for torque, and that's what we end up with. And then we put in this expression, which is, we have 1 over alpha. This is alpha. So 1 over alpha is going to be the inverse of this. So that the net torque is going to equal WF minus W omega, the initial, from final minus the initial, and we're going to put in this for alpha, but it's 1 over, so it inverts it, so it's going to be 2mr over 5. So if you put the numbers in, so you have 6.23 times 10 to the minus 5 minus 7.27 times 10 to the minus 5 times 2 times the mass of the Earth, which is 5.98 times 10 to the 24, The radius of the Earth is 6.376 times 10 to the 6th meters. And all of this will be divided by 5 times the force we're exerting. And you can see, because of these huge numbers up here, that this is a very small number, so that T ends up being 3.96 times 10 to the 18 seconds, or 1.25 times 10 to the 11th years. I'm sorry for the confusion up here. When we got to this point, T is not torque, it's time. So time, if you rearrange this equation, time is equal to this. Then you substitute this in for alpha here, and you get time is equal to this. Then you put your numbers in. Sorry for that confusion. 22. Now we're going to talk about rotational kinetic energy and translational kinetic energy. So rotational kinetic energy is equal to 1/2 I omega squared, and translational kinetic energy is equal to 1/2 mv squared. So we need to keep that straight as we do these kind of problems. Let me say that again. When it says that it rolls, we're talking about rotational energy. It says it doesn't slip, so it doesn't lose. It has both rotational energy and translational energy. And so the change in gravitational potential energy has to be equal to the sum of the rotational kinetic energy and the translational kinetic energy. And so that means that mgh has to equal 1/2 I omega squared plus 1/2 mv squared. So if we change this I here using the formula for that, we get mr squared, and then we put in v squared over r squared for omega squared. We keep this intact here. So we're converting everything to masses and linear velocities. And what you see is, first of all, you see that this m, and this m are all canceled out. This r squared is gone. And so what you have is GH is equal to 1/2 v squared plus 1/2 v squared, or v squared. And so that means that v is equal to GH. The square root of GH, which is the square root of 9.8 times 5, which is 490. And so V is equal to 22.1 meters per second. Now the key here is that you have both rotational and kinetic translational kinetic energy happening. You have both. As this thing rolls down this hill, it's rolling and it's moving this way. And so you have to take that into account in terms of both its rotational kinetic energy and its translational kinetic energy. And there's a difference in what happens depending on whether both of those things are occurring or just one or the other. Another problem like this is problem number 24. Number 24 states, calculate the rotational kinetic energy in the motorcycle wheel, which is shown in this diagram 10.38. And by the way, you're supposed to use the values for R1, R2, and in the problem number 15, which tells you what those values are. And it says to calculate the rotational kinetic energy if it's moving at an angular velocity of 120 radians per second. As it turns out, the R1 is equal to 0.280 meters. R2 is equal to 0.330 meters. And the mass of the wheel is 12 kilos. And so rotational kinetic energy is equal to 1/2 I omega squared, which is equal to 1/2, and the formula in this for rotational is m/2 times R1 squared plus R2 squared and then that's times omega squared now. And so we have 1/2 times 12.0 over 2 times 0.280 squared plus 0.330 squared times 120 squared. So if we put all the numbers in there and shake our calculator real hard, we get 8100. And the units for rotational kinetic energy are the same. They are joules. Number 25. A baseball pitcher throws the ball with a motion where there is a rotation of the forearm about the elbow joint as well as other movements. If the linear velocity of the ball relative to the elbow joint is 20 meters per second at a distance of 0.480 meters from the elbow, and the moment of inertia of the forearm is 0.500 kilogram meter squared, what is the rotational kinetic energy of the forearm? Rotational kinetic energy is equal to 1/2 I omega squared. So we have to convert this to this. That's what this all is all about. So this is going to be 1/2 times 0.5 times, and omega is V over R. So V is 20 and R is 0.48 squared. And if you do that, you get 434 joules of energy. Last problem, number 28. A ball with an initial velocity of 8 meters per second, so that's a linear velocity of 8 meters per second, rolls up a hill without slipping. Treating the ball as a spherical shell, calculate the vertical height it reaches. So I here, for spherical shells, is 2/3 mr squared. So we know that KE, rotational, is equal to gravity. And so 1/2 mv squared is equal to, 1/2 I omega squared is equal to P of gravity. And so 1/2 times 2/3 mr squared times v over r squared is equal to mgh. So 1/3 v squared is equal to gh. And now we're solving this equation for h. So h equals v squared over 3 times g, which is equal to 20 squared over, 8 squared, where I got 20, 8 squared over 3 times 9.8. So 64 divided by 9.8 times 3, that's 2.18 meters. Now the second problem, part of this problem, says instead of this ball rolling up the hill, it slides up the hill without rolling. So that changes this to KE kinet translational. And so it's 1/2 mv squared is equal to mgh. And then you cancel the m's out. Solve for h, you get v squared over 2h instead of 3g, or 2g instead of 3g. So that's going to be 64 over 2 times 9.8. So it reaches a greater height of 3.27.